Hello everyone, I'm Suchita Pati, a graduate student from University of Wisconsin-Madison, and in this talk I will be presenting our work on SeqPoint, a technique to identify representative iterations of sequence-based neural networks. This work was done in collaboration with AMD Research. To highlight the significance of the applications our work focuses on, I would like to start with the statement in Hindi, which most of us, including some of the native Hindi speakers, would find hard to interpret. But thanks to Google Translate, I was able to translate the sentence to English almost instantaneously. And there are two key points that I'd like to highlight here. First, as the sentence itself suggests, deep neural networks are ubiquitous today. And second, important applications such as Google Translate are enabled by DNNs. And we call these DNNs, which are used to process and predict sequences of information, sequence-based neural networks. SQNN-based applications such as translation, speech recognition, and sentiment analysis have seen a rise in demand in the past few years, which in turn has called forth the need to build efficient systems for them. And one of the key steps in designing efficient systems for applications has been the detailed profiling and characterization. These help system designers understand application requirements as well as bottlenecks in existing systems. However, profiling SQNN training comes with its own challenges, as SQNNs can take several hours to even weeks to train, which is further worsened by the overheads of profiling tools. Past work, such as detailed face detection, used for simulations while being extremely accurate, are too slow, and other works in the domain of DNNs approximate the profile by profiling only a few training iterations, which is fast but can lead to inaccurate representation in case of SQNNs. To overcome these drawbacks, we propose SeqPoint. SeqPoint clusters similar iterations together and identifies unique training iterations using simple and lightweight network-level parameters. This makes profiling up to 350x faster while being extremely accurate. This is the outline of the talk. First, I'll cover some background about SQNNs and training. I'll then motivate the problem in profiling SQNN training. Next, I'll provide some key insights that led us to our proposal. Finally, I'll describe SeqPoint and conclude with its evaluation. As briefly alluded to before, SQNNs are networks which process and predict sequences, such as textual sentences, audio, and video. There are two major classes of such SQNNs: recurrence-based ones, which include Google's Neural Machine Translation and Baidu's Deep Speech 2, and the other class being attention-based one, which includes models such as Transformer and BERT. Recent work from Google shows that recurrence-based neural networks have a significant contribution to the TPU data center footprint, thus making them an important class of workload to optimize for. In this work, we focus on recurrence-based networks, but the insights we draw and the methodology we propose can apply to attention-based networks as well. So there have been several prior work on deep neural networks. Then why look at SQNNs? SQNNs, compared to other networks, have unique characteristics. As briefly mentioned, these networks predominantly comprise of recurrent or attention layers, and these layers unroll or scale with the input sequence length, as shown in the figure below. The figure shows how a single RNN cell, when inputted with a sentence, unrolls as many times as there are words or steps in the input, while passing along information from one step to another. This is why we term these networks sequence-based neural networks. And this makes SQNNs different from CNNs. While CNNs process fixed size inputs throughout the course of training, SQNNs process inputs of varying sizes, making their iterations heterogeneous. Before going further, I would like to go over some of the training terminology that I will be using throughout the talk. Similar to other DNNs, SQNNs are also trained on a large input dataset. Inputs in this dataset are usually batched, with each batch containing a set of inputs. The model is then trained on a single batch of input at a time, and we call a single forward and backward pass of the model with a batch of input as an iteration. The model is trained on all the batches of inputs until the dataset is exhausted, and this is known as an epoch. Training usually comprises of multiple such epochs over the same dataset, with some optional shuffling between the epochs. With that background, I'll now go over the motivation for our work. Workload profiling is a key step that has guided system design, be it for software, compiler, operating systems, or hardware, and therefore it is a necessary step in building efficient systems for SQNNs as well. However, SQNN training is usually extremely long-running, with each epoch taking several hours to days, and this runtime only scales with larger datasets and deeper models, both required for better accuracy. Moreover, profiling tools have their own overheads in terms of runtime, memory, and disk, which again scales with application runtime, as well as the amount of information one collects using these tools. This makes profiling SQNN training extremely expensive. Some of the prior work in this area try to address this, but are usually expensive or inaccurate. There are several works on detailed phase detection, such as SeqPoint, GTPin, which are useful for hardware simulations, but involve expensive techniques such as function simulations, which can have large overheads. Some other work have focused on profiling individual layers instead of end-to-end models. But as you can see from the snippet of GNMT model here, SQNNs have heterogeneous layers consisting of different types of RNNs, residual connections, attention, and softmax layers. And understanding end-to-end models is crucial for understanding where the bottlenecks really lie and do cross-layer optimizations. Finally, there are other works which profile end-to-end models but approximate the profile with a single or a few iterations. This works well for CNNs because, as we showed earlier, they have homogeneous training iterations. SQNNs, on the other hand, have heterogeneous iterations, further highlighted by the figure here. This plot shows average architectural stats for a few iterations of GNMT. As you can see from the plot, these stats can vary by up to 30% across iterations, making profiling of a single or a few iterations inaccurate. So how to best profile SQNN training? Before describing a proposal, I'll go over some of the key insights that led us to SeqPoint. From our understanding so far, profiling a single iteration is inaccurate and profiling all iterations is expensive. In this case, the obvious step is to profile all unique iterations in an epoch. Note that since iterations repeat across epochs, we focus on profiling only a single epoch of training. This leads to three key questions. What determines the uniqueness of an iteration? How do we identify these unique iterations without additional overheads? And should we be profiling all unique iterations in training? I will answer each of these questions in the following slides. For the first question of what determines the uniqueness of an iteration, we call an iteration unique if it has a unique execution profile. And we define execution profile as all the unique kernels invoked and their runtime contributions. This is equivalent to program behavior and input size respectively, both of which dictate hardware behavior. Coming to the next question of what causes these iterations to be unique and how can we identify them without overheads. There are several factors that can affect the execution profile of training iterations. While network hyperparameters such as number of layers, hidden state size, batch size remain constant throughout training, the input parameters, specifically the sequence length, can vary across iterations. We therefore study the impact of sequence length on the execution profile and make the following three key observations. We first observe that the same operation across iterations can have different input sizes. In this table, we specifically show input dimensions of matrix multiplication or gem operations of two different GNMT layers for two different iterations. As can be seen, the dimension n of these gems can vary significantly across iterations of different sequence lengths. This happens as SQNNs can consist of layers such as the attention layer and the classification layer, which process entire sequences at the same time. Second, we observe that the type of kernels invoked across iterations with different sequence lengths can also differ. The plot here shows the percentage of unique kernels that are common and that differ between two iterations of GNMT. The first bar, for example, shows that there can be up to 20% of the kernels which are unique to either of the iterations. This happens as the network can invoke different operations depending on the input size, and it can also invoke the same operation but optimized for different input sizes. Third, we observe that the overall execution profile differs based on the input sequence length. The figure here shows the runtime breakdown of two GNMT iterations with different sequence lengths. And as is evident, the proportion of kernels such as the scalar operation and the reduce operation differ significantly across the two iterations. This happens partly due to the previous two observations, but also due to the nature of layers within the model. While some layers process entire sequences and invoke a constant number of kernels across iterations, some layers unroll with sequence length, and the number of kernels invoked are proportional to the sequence lengths. With these observations, we draw the key insight that sequence length is a key determinant of heterogeneity in training iterations, and we can use it to identify unique iterations. The final question that remains is whether we should be profiling all unique training iterations. To motivate why this is an important question, the plot here shows a distribution of sequence lengths in one of the datasets we have used for GNMT. As you can see, the range of sequence lengths in these datasets can be quite large. Moreover, the number of unique sequence lengths in these datasets can also be quite large. For example, in a deep speech 2 dataset, we observe that 50% of the iterations have a unique sequence length, and therefore profiling all unique training iterations would still require profiling half the training epoch, which could still be hours to days long. This brings me to our fifth observation, that iterations with sequence lengths close to each other have similar execution profiles. This can be observed in the plots here. The first plot shows the proportion of various kernels for four different sequence lengths, in which pairs of sequence lengths are similar. As you can see, the proportion of kernels in profiles of the sequence lengths within a pair are very similar. Moreover, in the plot on the right, we show the normalized runtime of iterations sorted by the sequence lengths. And as we can see, while the runtimes can differ by over 30x, runtimes of sequence lengths close to each other are very similar. This observation provides us with our second insight, that we can faithfully represent the execution profile of several similar sequence length iterations with only a single iteration. Having answered these three key questions, we now describe SeqPoint. SeqPoint uses a SymPoint-like technique to identify unique and representative training iterations. The insight that sequence length is a key factor determining the heterogeneity provides us with a lightweight metric to identify unique iterations. And the insight that similar sequence lengths have similar execution profiles helps us identify a small set of unique iterations to faithfully represent the entire SQNN training. I will now present the methodology using simple illustrations. The basic idea behind SeqPoint is, given a distribution of sequence lengths in the training run, as shown here, to bin it into a number of clusters. Then we find a representative sequence length from within a cluster such that its runtime is close to the average of the cluster runtime, and we assign it a weight corresponding to the size of the cluster it belongs to. We then use this equation at the bottom to project the total training time, and we find the error between the actual and the projected training time. If this error is greater than the threshold set by the user, we increase the number of clusters and repeat the process until this error is equal to or below the threshold. We call these cluster representatives the seq points. Note that there is a trade-off between the error threshold and the number of seq points, and thus the profiling time. So the profiling time can be traded off for a higher accuracy and vice versa. With that, I will now evaluate the efficacy of SeqPoint in profiling SQNNs. To evaluate SeqPoint, we use GNMT with the IWSLT 2015 dataset and Deep Speech 2 with the LibriSpeech dataset, both with a batch size of 64. We train these models on an AMD Threadripper system with a Radeon Vega 10 Frontier GPU with 16 GB HBM memory. We use TensorFlow version 1.14 and the AMD ROCm stack 2.4 for all our studies. Note, however, that SeqPoint is independent of the underlying hardware or software stack. We evaluate SeqPoint on its accuracy to project the absolute total training time, which is a key metric in evaluating systems for DNN training. We identify SeqPoints on a single hardware configuration and project the training times for different hardware configurations listed in the table below. This is done to test if the identified SeqPoints are independent of the hardware they are identified on. We also evaluate SeqPoint's capability to capture hardware behavior of the entire training run. To do that, we measure SeqPoint's accuracy in projecting the change in performance as we vary the underlying hardware configurations. We compare the errors in projections using SeqPoints against that of using a single iteration. We select the most frequently occurring sequence length, labeled as frequent, and we also show the worst case error if choosing a single random iteration. We label this as worst. We also compared SeqPoint with prior work, which profile a set of contiguous iterations. We label this as prior. To create the different configurations, we modify a single hardware feature, such as the number of compute units, the L1 cache, the L2 cache, and so on. Before looking at SeqPoint's accuracy, we first highlight the reduction in profiling time we achieved with SeqPoint. The plot here shows that SeqPoint methodology reduces the total number of training iterations that need to be profiled by about 50 to 140 times. This translates to a 215 to 345x reduction in profiling time. These speedups in profiling will be higher if training on a larger dataset, but with a similar sequence length range. Here we show SeqPoint's accuracy in projecting absolute training time on multiple configurations. Specifically, here we plot the error in projecting runtimes using all the techniques for GNMT. And as can be seen, SeqPoint is extremely accurate compared to other techniques with a maximum error of only 1.15%. Moreover, this also implies that SeqPoints identified using a single configuration can be used to project runtimes for other hardware configurations as well. Next, we compare SeqPoint's ability in projecting speedups with changing hardware configurations. Here we plot the difference between the projected and the actual speedups. Similar to the previous plots, SeqPoint outperforms other techniques in projecting speedups, implying that SeqPoints are able to capture the hardware sensitivity of the entire training run. Plots in this slide show the errors in projecting total training time and speedups using SeqPoint for Deep Speech 2. Similar to the case with GNMT, SeqPoint outperforms other techniques in projecting both these metrics for Deep Speech 2, with a maximum error of 0.33 and 0.41% only. To conclude, we showed that sequence-based neural networks and the applications they are used for are a crucial class of workload to optimize for. However, profiling and understanding SQNN training behavior remains challenging. Unlike convolutional neural networks, their input size dependent nature makes training iterations heterogeneous, requiring profiling of several thousands of iterations to get a representative execution profile. We propose SeqPoint using the insight that the heterogeneity is caused by the input sequence length, and that similar sequence length iterations have similar execution profiles. SeqPoint thus spins the large sequence length space and identifies a representative from each pin. We propose that executing and profiling iterations with just these sequence lengths, which we call SeqPoints, leads to several orders of profiling speedups while providing a faithful representation of the entire training execution. Thank you for tuning in.